Hi, today we are going to look at circular motion. We will see the uniform circular motion, and surely Jay will come up with an example that will help us reinforce what we've studied. Let's see what Jay proposes us this time. Jay is making a circular motion with the ball with constant speed and counterclockwise direction. Let's remember the characteristics of a circular motion. The velocity changes in direction and sense, as does the tangent vector. Therefore, as the normal acceleration depends on the derivative of the tangent vector with respect to time, it will be non-zero. Let us also recall the characteristics of uniform motion. The velocity is constant, and therefore the tangential acceleration is zero. In this case, the normal acceleration is constant. Note that the velocity is constant in magnitude, but not in direction and sense. Let us now obtain the equation that gives us the position on the trajectory at each instant. We take into account that the velocity is constant and equal to v sub 0. From the expression that appears on the screen, we separate variables, integrate as we usually do, and obtain the path traveled on the trajectory s as a function of time, where s sub 0 and v sub 0 are the initial conditions. We have obtained the displacement over the trajectory. If this displacement is made between point P1 and P2, the relation that exists between the displacement s, the radius r, and the angle that covers this displacement is s equal to r times theta. This angle is measured in radians. If we derive this expression with respect to time, we obtain that the velocity is equal to r times the derivative of theta with respect to time. This derivative is the angular velocity, which is measured in radians per second, and in this case is equal to omega sub 0. If we express the linear velocity as a function of this magnitude, we obtain that v is equal to r times omega sub 0 times the unit vector t. This vector, omega, must have a direction, a sense, and of course a magnitude. The direction of omega will be perpendicular to the plane in which the motion takes place. If the direction of motion is counterclockwise, the direction of omega, according to the right-hand rule, will be upward in this case. The modulus is v divided by r. We have defined angular velocity as the derivative of theta with respect to time. Similarly, we define angular acceleration as the derivative of omega with respect to time, and is measured in radians per second squared. In the case of a circular and uniform motion, omega is constant, equal to omega sub 0, and therefore the angular acceleration will be 0. If we express the intrinsic components of the acceleration as a function of these quantities, we obtain that the tangential acceleration is equal to r times alpha, and in this case is 0. The normal acceleration can be expressed as r times omega squared. In this case, a sub n will be constant. Let's see now the equation that gives us the swept angle at each instant. We start from the expression that relates theta to omega, separate variables. Integrate as we usually do, and obtain theta as a function of t. Theta sub 0 and omega sub 0 are the initial conditions. Therefore, in a circular and uniform motion, the angular acceleration is 0, the angular velocity is constant, and the angular displacement depends on time. Omega sub 0 and theta sub 0 are the initial conditions. Now we are going to represent the kinematic diagrams, omega versus time and theta versus time. If we represent the angular velocity, omega versus time, we obtain a horizontal line. The area contained under it in a time interval is the displacement made by the ball in said interval. If we represent theta versus time, we obtain a line whose slope gives us the value of the angular velocity. It is time for Jay to give us his example. Jay is moving the ball counterclockwise, describing a circle of radius 1 meter. I concentrate on the 0.000 according to the reference system shown in the figure. At the initial instant, the ball is at 0.10 and carries a constant angular velocity of 0.25 pi radians per second. He asks us to determine the time it takes the ball to travel half a circle, the path traveled in that time, the linear velocity of the ball at the point 0 minus 1, 0, the tangential and normal components of the acceleration at that point, and to draw the acceleration vector at the requested point. We start from the data given in the problem, we take into account the expressions we have found in the class, and we get ready to solve the problem. The first thing we are asked is the time it takes to travel half a circle. Half a circle corresponds to a theta angle of pi radians. Therefore, from the expression that appears and taking into account the data of theta and omega sub 0, we find the time obtaining that the elapsed time is 4 seconds. The path traveled is calculated from the relationship between the path s and the angle theta. We substitute values and obtain that the path traveled is pi meters. Let us now calculate the linear velocity from the relationship between v and omega. Substitute values and we obtain that the velocity is 0.25 pi meters per second. This is the magnitude of the velocity because the velocity as a vector will be changing at each point. The magnitude is constant, so it is a circular and uniform motion. Let us now find the components of the acceleration. The tangential acceleration is 0, and the normal acceleration will be calculated from the expression. A sub n equals v squared divided by r. It remains only to represent the acceleration vector. It has only normal component. And the sense is towards the inside of the circle and the direction perpendicular to the tangent at the point. Well, the time has come for Amanda to remind us of what we have studied in this class. We have seen circular and uniform motion. In this, omega is constant, the angular acceleration is 0, and the tangential acceleration is 0. The normal acceleration is always non-zero. We have also obtained the relationship between linear and angular quantities. We have also obtained the path traveled on the trajectory as a function of time and the swept angle as a function of time. That's all. See you in the next class.